Hello, this is the first PowerPoint which will discuss the first topic, which, as I stated in my introduction PowerPoint, and I will talk about filler content and geometry in this presentation. So, quick review on the chemical properties, applications, and concerns of PTFE. First of all, PTFE is a short form, it stands for polytetrafluoroethylene. Um, This is the chemical structure of PTFE. You have carbon and carbon bonded to each other covalently, and each carbon atom is further covalently bonded to two fluorine atoms. And this, whatever you see inside the parenthesis, keeps repeating to form a long chain, and that N is basically representing that this is a repeating unit and keeps repeating to form a very long chain. The applications of PTFE are sliding and dry lubrication. The properties which allow PTFE to be used for these applications are its high melting temperature, low friction coefficient, and chemical inertness. The main concern, however, with the use of PTFE is that it has undesirably high wear rates, roughly on the order of magnitude 10 to the negative 3 mm³ per nm, and that makes it less durable to be used for extensive periods of usage. Therefore, over the years, a lot of different research groups have tried to improve the wear rate of PTFE and also try to explain the mechanisms that are involved in the improved wear rates of PTFE. So in this presentation, I will be covering four topics: filler size, filler shape, filler concentration, and filler functionality. Now, filler size and filler shape are very interesting and important topics as they are interrelated, and you will see how they're interrelated when I discuss them. Beginning with the first topic, filler size. Here in this study, the research group compared two different ranges of um, filler sizes. So they tested the microscale fillers and the nanoscale fillers. So the microscale fillers are 1,000 times bigger in size as compared to nanoscale fillers. And when I say fillers, I mean particles that are mixed with the PTFE to form a composite. And the nanocomposites and the microcomposites are made from alumina, which is Al2O3, chemically speaking. Now, if you look at the images from the electron microscope, you can see that the micro-scaled particles are much bigger than the finer nanoscaled particles. These results are very clear as they indicate that there's a huge gap between the performance in terms of the wear of PTFE, unfilled PTFE, microcomposites, and nanocomposites. So the unfilled PTFE performed the worst in terms of wear rate, whereas the nanocomposites performed the best. They were in the ultra low wear range, 10 to the negative 7 mm³ per nm, whereas the microcomposites were 10 to the negative 5 mm³ per nm. In terms of the friction coefficient values, there was not much drastic difference in the values of friction coefficient as compared to the values for changing particle sizes. So although there was some difference, but there was not such a huge difference as was seen for the case of wear rates. Now this group suggests a mechanism that is involved in this difference in the wear rates that was seen. Now, before I talk about this mechanism, I will first have to explain something called a transfer film. And this is a very important explanation because in almost all the studies that I've reviewed, uh, all research groups have looked at this transfer film, its evolution over time, and its evolution over time. Now, a transfer film is basically a layer of PTFE that basically gets transferred from your PTFE composite onto the counterface. And it is an important link, it is an important factor in understanding how the wear rate of PTFE and its composites are affected. So now that we know what a transfer film is, now we can talk about the mechanisms. So this group suggests something called differential surface abrasiveness. Simply speaking, what they're trying to say is that the nanocomposites are not as abrasive to the transfer film as compared to the microcomposites. As you can see clearly from these electron microscope images, the transfer film for the nanocomposite is smoother as compared to the flaky, abraded surface of the microcomposite. Um, so this group is saying that because of this difference in abrasion, um, difference in abrasiveness of the composites, um, nanocomposites are allowing even better stability of the formed transfer films, thus producing decreased smaller wear rates. The next group looks at the shape of the fillers. So basically, instead of using regular spherical shaped particles, they're using irregular shaped alumina. Again, here we'll be looking at the nanoscaled version, 80 nm average particle size, and here they have changed in this study they've changed the percentage of alumina in the PTFE matrix. So these are the results. Clearly, the best performing candidate was the 80 nm Al2O3, as it produced wear rates of about 10 to the negative 7 mm cube per nm. In terms of the friction values, there was not a drastic difference in the friction values. However, the 5 weight percent filler performed slightly better than the other fillers because it was the low it provided the lowest friction coefficient values. Now, this group suggests another mechanism that is involved. Before I talk about that, we'll look at the wear rates. Um, Even a little bit more carefully. The regular shaped nanoparticles um, have a wear rate of about 1.6 times 10 to the negative 6. Now, in this study, they did not actually report this wear rate because they didn't study the wear of regular shaped nanoparticles. This value was obtained from another study, and that study is basically the next topic, the filler concentration topic, which I'll be talking next. That research group provided this value. So as compared to the regular shaped nanoparticles, the irregular shaped nanoparticles perform 10 times better than the regular shaped particles, and this group suggests that the reason for this improved performance is that the irregular shaped particles have a faceted nature, and this faceted nature allows greater contact surface contact area for more mechanical entanglement to occur and a more adhered transfer film to form. And again, the adherement of the transfer film and stability of the transfer film are important to have improved wear rates. This is the third topic that I'll be discussing, which is the filler concentration. So in this study, the research group changed the filler concentration from 0% to 20%, and this is the study which reports this particular value, 1.6 times 10 to the negative 6. So they changed the value from 0 to 20%, and they used alumina as their filler, and the size of the filler approximately was close to 38 nm. So these are the results. Clearly, you can see that increasing the weight percent of alumina causes a decrease in the wear rate, and this decrease is monotonic. So that's an interesting result. On the other hand, for the friction coefficient values, there was not much change in the values of friction with the change in weight percent of alumina. So they both of them are weakly dependent on each other. Now, why is this the case? So this group suggests a different mechanism. So they looked at the tribo surface using the scanning electron microscope, which basically is what SEM stands for, and they produced this image, which basically suggests that um, there are islands of PTFE. So this is the PTFE material, and there are and which are surrounded by the alumina nanoparticles. Now, because of these islands of PTFE surrounded by the alumina nanoparticles, there's no direct contact between two consecutive islands of PTFE. So because there's no contact between them, there's no direct contact. If any if any particular PTFE island gets damaged during sliding, then the other islands are not affected because of this disconnect. And as you can recollect from this graph, there's a monotonic decrease, meaning um, increasing weight percent of Al2O3 decrease the wear rate monotonically. So what this suggests, and what that graph and this image suggests, that if you increase the amount of alumina particles, then there's even greater discontinuity between this PTFE island and another PTFE island. So this increase in disconnect would cause the wear to go even down because of an even further disconnect between two PTFE islands. So the damage will not easily transform from island to island. Now, the final study in this particular presentation that I'll be looking at talks about filler functionality, and this is related to the filler size, and you will see how as I talk about it um, in detail in future slides. So they had 5 alumina samples: A, B, C, D, and E, and these are the vendors from where they purchased these samples, and these are the vendor reported sizes. Now keep this in mind, because this is a very important. These numbers are very important. As you can see, this graph is SLS graph, which basically stands for static light scattering, and as compared to what the vendors suggest the sizes of the particles are, the graph or this image is telling us a completely different story. Look at this, for instance, for alumina E. The vendor says that the size is in the range of 27 to 43 nanometers. But if you look at this graph, the size of alumina is in the range of 1 to 10 micrometers. So there's a huge discrepancy, a huge difference in what the vendor is saying and what the experiments are showing. Even if you look at the other alumina D, for example, alumina D again is in the range of 1 to 10 micrometers, whereas the supplier is saying that it's in the range of 27 to 43 nanometers. Even further proof of this discrepancy is found when you take the electron microscope images for alumina E. So if you look at the resolution, this is 10 micrometers resolution. So if it was so small, if the alumina particles were so small as stated by the vendor, then you should have seen much more smaller sized particles on a 10 micrometer scale. But they are lumps. As you can see, they are large lumps of PTFE, of alumina particles. And if you zoom it even further, you can see that these are uh, porous particles. Now, this is very important to understand what is going on. Uh, what this research group suggested was that these values that the vendor reported came from something called BET method of calculating the values of particles. So this d and m is basically the diameter in terms of nanometers of the particle, and this equation is basically what you can use to find the value of, or the size of the value of the particles. So these, and now let's look at these values. So now clearly this table shows you the huge difference in what's going on. So alumina B, A, B, C, D, E, these are the vendor reported sizes in terms of nanometers, and the BET method, which basically using this equation, um, you can find the size of the particle. So if you look at these results here, 206, 160, 183, 76, and 39. So the BET method is giving values that are very close to what the vendor reported particle size is. So probably the vendors used this method, the BET method, to approximate the size of the particles. On the other hand, the actual experimental results of SLS, static light scattering method, gave these values: 267, 375, 781, 1311, and 3950. So these values, there's a huge difference between um, the scale or the order of magnitude uh, as reported by the vendor. So this, if you look at this value, this is 1.3 micrometers in size, and this is 27 to 43 nanometers in size, so 1,000 times different. Um, so you can see that the vendor reported sizes are not correct, and the group gives a reason as to why this difference is occurring. This image tells the story. The porosity is an important factor. Now, this equation can be used um, only if certain assumptions are met, and in the assumptions, the particles have to be dense and non-porous, whereas here clearly the particles are porous, and therefore this equation cannot be used to estimate the size of the particles. Now, moving on to X-ray tomography and TEM images. TEM basically stands for transmission electron microscope images of alumina E. Now, this is a very important and interesting study, because this talks about these images basically um, explain what is going on at the wedge surface. So basically, these images are trying to show you that the micro-sized particles are breaking down into nano-sized particles, because and this is for alumina E. So we know from the SLS that alumina E had a median particle size of 3950. It did not have a it did not have a particle size of 27 to 43 nm, as what the vendor said. So these images suggest that these alumina particles are breaking down to form. So initially you have alumina rich running film, and if you zoom in further, you can see that this film breaks down to fine scale alumina. And this X-ray microtomography shows you the distribution of the alumina. So here you have a dense region of alumina, and you have you have a dense fine region of alumina, and here you have the bulk alumina. Now, results for wear rates. So this group looked at the supply designated particle size. So in the sense, right now in this study, they are basically looking at the wear rate as compared to what the suppliers said. So the suppliers said that the lowest wear rates would be seen for alumina with the lowest particle size, and the highest wear rates will be seen for the particles with highest particle size. And these are the wear results. They also compared it with some previous studies. So you can see clearly that the alumina D and alumina E have the lowest wear rate, roughly in the range of 10 to the negative 7 mm cube per nm. I'm sorry, even alumina C has similar wear rates. Now, why is this wear reduction occurring? Now, the research group suggests what's going on actually is that um, alumina microcomposite, which is basically the actual size of the alumina as stated in this table, 3950 mm cube, 3950 nanometers. So alumina C, D, and E have approximately very high sizes: 0.7 micrometers, 1.3 micrometers, and 3.9 micrometers. So this large sized particles are basically breaking down when sliding is occurring. So during sliding, because of the increased stresses when they come in contact with the counterface material, they break down to form even refined and smaller scaled particles, which are basically very close to the nano range. So it's not so as you so as you looked at the earlier studies, it's not actually the size of the fillers that is involved in the process of decreasing the wear rates. It's actually the breaking down of the, it's basically the transformation of the fillers from micro scale to nano scale during sliding, which is involved in the decrease in wear. Because although the first group, this filler size group, suggested that there's a difference between the abrasion or the abrasiveness of the fillers. So, and this group is also stating the same thing, but they're saying that the microscaled particles break down to form nanoscaled particles, which in turn makes them less abrasive to the surface and forms more stable transfer films, and thus is involved in the um, reduction in wear rate. Now let's look at the overall summary of all the work that I've reviewed in the past few slides. Looking at the friction values, it was clear that changing the filler size, filler shape, filler concentration um, did not drastically affect the sizes, affect the values of the friction um, of the as compared to the unfilled PTFE. So unfilled PTFE roughly had a friction coefficient of 0.18, and changing your different parameters did not change the value by a lot, as was seen from the studies. On the other hand, wear rates that were seen were very sensitive to the parameters. So changing the filler size affected the wear rates, in the sense going from micro to nano range affected the wear rates. Then changing the wear concentration monotonically decreased the wear rates. Then changing the wear um, changing the shape of the filler also affected the wear rates by improving the wear rates 10 times for the irregular shape. So as you can see already, this is only the first topic that I'm presenting. There are two other topics that I will be presenting. But as you can see already, there are so many factors and so many different mechanisms that are interrelated, that are going into the wear process and wear mechanism. So you can probably imagine how complex the involvement of these parameters would be, and a lot of research still has to be done to understand exactly what is going on at the surface. Thank you for listening, and I will probably see you in the next PowerPoints. And before closing, I would just like to acknowledge Miami University Library Resources, Google Scholar, because I have found my articles from these two places, and also Calcutta recording tool, which I'm using right now to um, record my presentation. Thank you.